Okay, so let me begin from. So we are studying dimensional, ideal, incompressible. This is, in fact, more practical than it looks, because the most important fluids like atmosphere and ocean are nearly two-dimensional. Yeah, so the expanse in horizontal direction is much larger than vertical. And we can observe very beautiful through pictures in atmospheres, say, of Jupiter and Saturn, if you like, and even of Earth. On one hand. On the other hand, it is the most fundamental model of continuous medium, because actually it bears no material characteristics. Yeah. So as Victor Yudovich said that it has only one property: to occupy the space, nothing more. So it is next to just a material point, and next in its fundamentality. Okay, and so we can consider it from different viewpoints, or consider different, first of all, which problems here with ideal incompressible fluid. This is like with any other fluid problems. Initial value problem, no, given initial velocity, find the further motion. It's clear. Second problem is two-point problem. So what it is? This is our domain where the flow goes on. In this domain, the fluid moves. Fluid is a collection of fluid particles. Every fluid particle has some trajectory, and suppose the particle initially at the point x, and then after some time t, it is the point y equals, say, f of x. Yes, and this matrix x to y is a fluid configuration. Fluid configuration. So position of every fluid particle. And so the two-point problem is two-point equal to fluid configurations. F, G, find the flow connecting them. Connecting means that every point which was initially at the point f of x finally reach the point g of x. Yeah. And the third, much less studied, is I would say ancient flows. What is this? Suppose that the flow happens, it started long ago, and it does not finish, it proceeds for indefinite time in the future, like in the nature, say, in the atmosphere and ocean. Yes, and we are interested to know something about this flow. Yes, so this problem looks quite vague, but in fact, if I say or write the keyword attractor, the situation comes in perfect position. We have some dynamical system. The fluid, after all, is a dynamical system. Yes, dynamical system happens in some phase space, and in this phase space can appear attractor of this. In some sense, this or that sense. Yes, there are different adjectives for attractor. So the study of ancient flows is, in fact, the study of attractors. Because if the flow was going on for infinite time before, then we certainly are on attractor, and we are moving along attractor. Yeah? So the study of attractors is the study of these ancient flows. Yeah. No, okay. So it is the problems. Now, let me say I would say setups. First, Eulerian. Eulerian, this means that we study the velocity field, which is described by the Euler equation. Lagrangian. So we study the motion of fluid particles. Yes? And third is Hamiltonian. It is, we study together the pair of position and velocity of fluid particles, or momentum. Yes? So they, no, okay, there is brilliant theory, say, algebraic and geometrical viewpoint from on all these things from the side of a group of the theory and so on, which I am not going to go deep into. You will, I hope, touch all three of them. And now, what are, say, the, how I call them, structures? Structures. So, in fact, in the fluid has a lot of structures in some sense. So let me just write a few of them. Mixing structure. Mixing structure. So the mixing is the usual property of fluid flows. Flows is mixing any additive. And it turns out that this mixing alone gives us interesting and non-trivial information about the flows. So we study the mixing properties. Second is an example of the structure is the following. It is a braid structure. What does it mean, braid structure? So I remind we consider two-dimensional fluid flows. Yeah. So let us consider the motion of fluid particle and add one more coordinate time. Yeah. So this is our flow domain M. This is then every fluid particles describes in this xt space some trajectory. Yeah. Other particle describes different trajectory. The third particle describes also some trajectory, and so on. And all this trajectory, what is the property? No, in normal situation, either any two for any two different particles, their paths don't intersect. Yes, they don't meet. If they say the fluid vector velocity field is smooth, then they don't meet. Yeah. If we have more less regular situation, then they can meet, but the probability of this event is zero. So almost all of them don't meet. Yeah. So these lines in the xt space in general don't meet one another, so they form a braid. No, the difference with what is known in topology is that this braid with continuum of threads. Yeah. So again, we have a rich structure of finite braids, and you can imagine that it is even richer in these continuous braids. So it is other structure which appears here. And I also want to study it. Next is analytical structure. It is related, I mean, real analytic. It is related to the striking discovery. It was relatively recent discovery, but in fact, it is, could be done even 90 years ago. Now it is 99 years ago by Liechtenstein himself. Look at the name of this room. That same Liechtenstein. He did not discover, but he was able to do it. It is the following thing. If you consider the trajectory of a fluid particle in the flow, yeah, it turns out that this curve is real analytic. It is real analytic, though even if the velocity field is not analytic and has some fine and very not very high regularity. Yes. So Uli Frisch called this situation very smooth ride in a stormy sea. Just imagine you have a stormy sea and your boat is moved along analytic way. Yes, please.
Is this special to the stationary flow?
Excuse me?
Is this special to the stationary flows?
No.
Also including.
Yes, yes. It is general fact for any solution of Euler.
Depending on T. So it could be unstationary and depending on t.
Depend on t, yes. Oh. Yes, so velocity field depends on t, any solution of Euler equation. Yes, so this is a striking result, and it's I would say relation to other results and to the general general situation with the fluid is still not clear how it is related, for example, to these ancient flows and attractors. I think there is some intimate connection. Fourth structure, it is in fact two related structure, quasi-linear and quasi-root structures. Yes, it is less known things. Just a few words. Consider, you know what? Let me not explain it now because it will distract us. So it is for the future. If we reach it, then I will explain. Yeah. So it is. There are other structures as well, but this depends on how much I will be able to tell. So open, truly open-ended situation. So let me start today from this mixing structure. Consider the so first of all, the Euler equation is the following. We have a velocity field U of xt and pressure field P of x. T plus gradient U got U plus gradient P equals 0. We consider usually the flow without external force. And divergence is equal to 0. It is the Euler equation. And now we consider vorticity. Omega equals vorticity of U. No, U, P, and omega are functions depend on x. So there's an Euler equation. Now we can transform them to vorticity formulation. Just for simplicity, I would say for my convenience, let us suppose that M, the domain where the fluid is moving, is simply connected. M in R2 and what? Okay. connected. The M is small. It's no boundary. And area of M equals 1. Then omega is curl u, and now if you know omega, then we introduce the following thing. Velocity field u equals u gradient of some function psi. Yes? What is psi? Psi is such a function. If like this, then omega equals curl psi equals Laplacian of psi. First of all, and we have the boundary condition for psi in psi on the M equals 0. No, it can be no equal any constant, but let us write 0. It doesn't matter. And then we can find that u equals u gradient of delta minus 1 of omega equals, let me write it, curl minus 1 omega. So what is delta minus 1? Delta minus 1 is a solution of corresponding Poisson equation with boundary condition, the boundary condition. Yeah. So this means that curl of u equal omega and un on the boundary equals 0. U equals curl minus 1 of psi omega. Okay, and with this we can write the following. No, now the Euler Lagrange Euler to Lagrange transition. So Euler equation is our variable is velocity field. Lagrange equation, our variable is the transformation from initial to position of every fluid particle to position at time t. Yes. So we have particle trajectory. X goes to say ft of x. Yeah. So f0 of x, say, equals x. And this ft has the following equation: d ft of x dt equals u of t of x. This is equation. If u is given, then you know this. Given velocity of the particle at every point, and u, say, yt equals d dt ft of x. X is ft minus y of y. Yeah. So to recover u from f, we have to find the velocity of the particle, which at the time t was at the point y. So this is the u, and now I want to write down vorticity transfer. Equation. I'm sorry, do you know all this stuff? So better to explain everything. Okay. Vorticity transport equation. It is the following. Suppose u xt is a solution of the Euler equation. And ft of x corresponding Lagrangian solution. Then curl u of xt equals curl u of ft minus 1. This means that if the particle we start from some point x, we take initial velocity phi and find the vorticity at this point x, and then this point f is traveling with the flow, and at the moment y it is at the point ft of x, then it brings the value of vorticity with it. No, vorticity is looks like the fluid is rotating around this point, yeah, and this small gyroscope moves together with the fluid. It is the vorticity transport equation, or it is called Kelvin-Helmholtz equation, or recently it became fashionable to call it Cauchy equation. Cauchy did not write this equation, but wrote equivalent equation. So it is a classical part which we will use now. So this means that if you have this flow ft, yes, so if you, one moment, if you fix, if you consider this ft, we have ft is a function of two variables, t and x. For fixed x, it is trajectory of a particle which initially was at the point x. If you fix t, it is a map from initial position of the fluid to position at the moment t. Yeah. So it is some map for fixed ft and f. And now what can be said about ft? You have an equation which was written at this point. Yes, that divergence of u is 0. Divergence u is 0. This, if u is, say, smooth velocity field, so after integration of velocity field, we have that Jacobian d ft of x dx Jacobian is identically 1. So it is why this fluid is called incompressible. It is because the area, in this case, area of any domain in the fluid, when it is moved by the flow, does not change. It is deformed, but it is not changed. And now let us forget for a while on the origin of this flow ft, whether it satisfies or not satisfies the some differential equation. Only this condition remains. Yeah. So we consider family, one parameter family of diffeomorphisms of our domain. For example, this domain is the interior of your cup of coffee, and you added some milk, and then you start to stir it with a spoon. Yes, and you see that the milk is mixed with the coffee. What does it mean? This means that this flow which is produced by the motion of the spoon is exactly the family of diffeomorphisms. Every particle of the your fluid is moving, yes, and this diffeomorphism become more and more complicated, more and more convoluted, and they very soon look like mixing. Yes, but mixing, what is mixing? You have to define what is mixing. Yes, and now let me forget for some time about the origin of this transformation, diffeomorphism, and so on. And even I forget about these diffeomorphisms. And now I want to start to explain what is general mixing. Mixing operator. So to study the mixing structure, first of all, we have to define what is mixing. Consider this domain M. And consider the space L2 of M has scalar functions. And consider the following operators, mixing operators. Operator K L2 of M defined by the following formula K f of x equals integral over M A x y f of y dv. Yeah, just integral operator. So operator K is called mixing with the following properties. The kernel K xy is non-negative. This means that in fact K is a non-negative measure. It can be not only the function of measure. Second, integral K xy dx is identically 1 as a function of y. And third, integral K xy dy is identically 1 as a function of x. Yeah. No, it is very familiar class of operators. They have different names. So this stochastic operator. Sometimes they call polymorphism. Polymorphisms. Yeah. Operators having these three properties. No, in particular, examples. First example is the following. Suppose that f or f is okay. Let me C M. M is area resolving diffeomorphisms. Suppose we take C area preserving diffeomorphism. Then consider the operator, the kernel K xy is delta function of y minus c minus 1 of x. Delta function. No, two-dimensional delta, because the domain is two-dimensional. This is so what does it make the function f? Okay, f of x equals, after you substitute it in the formula. In this formula, you have f of c minus 1 of x. Yeah, if you substitute it. This means that it is familiar thing. So the function f is translated by is transformed by this diffeomorphism f. So we make f, and the function is carried by this diffeomorphism. So it is what we already had before. The second example is the following. A x y identically 1. It also satisfies this. What does it mean? K f of x equals integral f of f dx. Mean value of no, without this, simply integral f of x dx. So it takes the function and makes it its mean value or integral. Yeah. Now, what the set of all mixing operators, okay, is denoted by beautiful p. Why p? Because polymorphisms. And so what can be said about this set of operators? Properties of p for p is a semigroup. This means that composition of two operators of p is operator of p. No, you can check it yourself. Second, p is convex in say operators, bounded operators in two of it is convex set of operations.
Sorry, 100%. Are you asking that exactly? You're also asking that K is such that the operator K
Yes.
sends L2 into L2, right?
Yes, yeah, of course.
Okay.
Of course,
So it should be like
they are
property 4.
bounded operators.
Yes.
Yes, bounded operators, positive, and so on. So K is convex. P is the compact. No, second. weakly precompact. This means that this means that if you have K1, K2, and so on, sequence of this operator, then you can form any G in N2. You can find a subsequence KIM such that K I and F G go to some limit. Next property.
But the subsequence doesn't depend on F and G, right? You find the
Subsequence, after all, does not depend because L2 is separable. You can use diagonal process. So, let's transform this statement this way. Next property is that it is contraction. KF equal to 1F. And 5, we had in this place examples of take C of goes to C minus 1. C is, by the way, I forgot to define notation. The set of transformation C M to M such that C is the diffeomorphism preserving area. Yeah, the set of such diffeomorphism is denoted by D. Yeah. C D. The set of operators take C F goes to F C minus 1 C in D is represents So why we have these properties of weak density and weak compactness? It is because, after all, K is operator with measure with kernel, which is positive measure, a positive normal measure, yeah, and the set of positive normal measure is compact in the no pre-compact in the space of measures. Yes.
What does weakly dense mean?
Excuse me?
What does weakly dense? What is weakly dense?
Weakly dense means that for any operator in P, there is a sequence of operators of this form, which weakly converges to this operator K.
Okay, through duality.
Yeah, weakly dense. Okay, so these are the properties which I will use from time to time. And now I want to proceed further. And the obvious thing that P is a semigroup of operators in L2 extent. So we have some set of operators such that the composition of operators is also in this set. And this operators operator in this Hilbert space. Every time when we have semigroup of transformation, any semigroup of transformation in any space, it defines a partial order. Order. So I introduce notation. So F is in this sense less than G if there exists operator K in E such that F is K applied to G. It is a partial order. This means that if F less than G and G less than H, then F less than H, because product of these operators in the polar group, a semigroup, is again in the same semigroup. Yeah. So this means we have a partial order. Every time when we have a partial order, we are interested in the minimal elements with respect to this partial order. But first we consider partial order. Let us return to our flow, the two-dimensional fluid. Yes. So if omega 1 equals curl U1, omega 2 is curl U2, we can write right, omega 1 less than omega 2 if there exists K such that omega 1 equals K omega 2. So I just repeated definition applied to this omega. Yeah. If omega 1 in this sense less than omega 2, and at the same time omega 2 less than omega 1, then we write, say omega 1 is equivalent to omega 2 in respect to this partial order. Not quite natural way of writing. No, it would be convenient to write U1 also less than U2 in this if curl U1 less than curl. So we lift this order from vorticities to the velocity field themselves. Now, if you have the Ft around flow, Ft is a family of transformations. Yes, then omega of Ft equals K Ft of just repeat where here was written what is Ft. It is the same property of vorticity transportation. So this means that omega t is omega 0. So we go down, but since our transformations Ft are smooth, they are invertible. Yes, this means that omega 0 is K Ft minus 1 omega t. And this means that that omega 0 less than omega t. Yeah. So omega t is equivalent omega 0. But uh, when we t goes to infinity, yes, our transformation in the weak sense tend to, or at least some subsequence, tend to some operator. So this operator kf t, when t goes to infinity, does not tend to operator of this form. It tends to some operator from K, some mixing operator, but which is not, maybe not operator of this form. Because this operator of this form are dense, weakly dense, yes? So it, in general, moves to weak closure of the set of this operator of transformation form. Yes?
Does it depend on which sequence of times? Does it depend, does the limit depend on the sequence of times?
May depend. It may depend. In general, it may depend. Yes. And so, now I want to consider some set of the flows. Flow, when I say flow, I mean either velocity field or vorticity field, something like this, depending on context. Both describe the flow, or even string function psi. It's all equivalent description of the flow. So consider the following set. Which I called given u. It is a good moment to introduce notation. D 0 equals set of u in L2 of M R such that it is incompressible in weak sense, and on the boundary is 0. So what does it mean? This and this. This means that the function u is orthogonal in L2 to all gradients. U is a vector function, the same as integral u of x times gradient phi of x. The x is 0 for any p in C infinity of x without boundary condition. So the function, the vector field is incompressible and tangent to the boundary in the weak sense if it is orthogonal to any gradient. If we assume that u is, say, in say C1, then we can find by integration by parts, find both these conditions.
Where does What is the space? L2M R?
R vector fields. Vector field, R2. Vector field, yes. So the V0 is this space. Vector field such that they are orthogonal. And V0 and V1 it was U in V0 such that U curve U in you know what, here I have I would say an inner conflict, because for simplicity I would write here AL2. Yes, so it is more or less H1. Yes, but for such vector fields, we cannot guarantee that the solution of the Euler equation exists and is unique. It is too wide space. So I have to use some smaller space. But at this moment, let me write in simply so. I will make adjustments later on. V1 is this. And so now define the following thing. Given U in V1. Omega U equals the set of V in V1 such that first V less than U in sense of curve. No, let me write once here. Curve V less than curve U, and norm V L2 square 1/2 equals 1/2 norm U L2 square. So what is this? If you follow the flow, then first there is no friction, no viscosity, and so the energy is conserved. Energy is 1/2 of square of L2 normal vector field. This is conserved. And for any finite C, the curve V is equivalent to curve U in the previous sense. It is not mixed, it is just deformed. But here we introduced also some closures of this, big closures of this. Yes, so it is a larger set, and in this set we will look for the limit elements. Yeah, so we have to find to extend here. Okay. So omega U inherits the partial order from what from V1. So for any two elements, we can say if one is less than other, or back, or none of them. And now we are interested in the minimal element. So let me write W is a minimal element of in this only the U. If the following is V. If the following is true, if I say V less than there is other element W is on the U, and W less than V, then V less than W, and hence V equivalent to W. So it is the what can be said about the minimal element? It should be there should be no other element which is strictly less. Yes, if it is at least not more, then they should be equivalent. Yeah.
Is it obvious that this always
Excuse me?
Is it obvious that always exists?
Obvious what?
That omega always exists.
Omega in W.
Yeah.
No, for
V.
Yeah.
V. So V, it is not obvious that such minimal element exists, and the next thing which I wanted to say.
Okay.
Minimal element of omega U exists. So how do they prove such things? So I have to, in this case, I have to use the zone law. Suppose S is a partial ordered set. There is
You know, you have a second blackboard behind.
excuse me?
You have a second blackboard behind. In
I-
principle, you
It's
know.
not convenient. Because if I lift that, I can't reach it. If I lower this, no, okay. Okay, let me try. No, this is abstract. Okay. I'm sorry. If I were longer, S is a partially ordered set. If I is a linearly ordered set. This means that for any two elements of I, there is a relation either I less than J or J less than I, or they are equal. Linearly ordered set. Sequence. Sequence is a family. Like this. Si the sequence is labeled by elements of I. Is called a chain if I less than J. It is linearly ordered set with order relation this simple like this. If I less than J implies as I less than J as I more than as J. So it is decreasing chain called decreasing. An element S subscript in S capital is a lower bound of the case Si if S sub bar is less than Si for any I. So if some element is less in the sense of our partial order than all element in the chain. Now, one them. If S is a partially ordered set, S in order relation such that for any decreasing chain Si, there exists a lower bound as subscript if then there exists minimal element no, S0 of F with this duration. No, it is one of central, most useful theorems in set theory, very general, and the proof of this theorem is long and does not enter my, let's say, program. I recall when I taught set theory, then it was, it took a couple of lectures. So let us take it as granted and consider the following our own example. What is interesting for us? But I wanted to stress there exist, but nobody says that it is unique. There can be many, of course. Let me consider our case. So S equals, what is S? Is omega. Yeah. S equals omega u. As defined by the action of the semigroup of polymorph in V0, V1. No, it acts on the vorticities. And here, what? I reach page 5 in my notes. All in all, we have about 33 pages for today's lecture. One girl was defending her coursework in front of committee. One girl student. Yes, at some point, examiner asked her, how much is remaining in your talk? She said about a half, but you have 5 minutes remaining for you. She says, never mind, I will talk faster. Yes, I'm not able to do it. Okay, so now the next thing, you prefer have 1.5 hours, astronomical hours, or 2 hours? Depends on your physical force.
I would prefer to have more lectures, like have a longer class, but have 90-minute lectures.
90 minutes lectures, 1 month. 60 plus 30 is 90, yeah?
Yeah, sorry, an hour and a half, sorry.
So this means that our lecture is over in 5 minutes. Okay, if you agree, I will do it and next time try to talk faster. Okay? Okay, so next time the same place. I asked to bring me another box of chalk, and I did not find even one piece. It's a shame. No, okay, I don't want to kill you. By the way, is it familiar stuff, the zone lemma?
Yes.
Familiar, so I can use it freely. You know what? It is a pity. Let me tell you in few words how this theorem is proved. So with all this background, I use the same notations. So suppose uh, 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 is hy- hypothetical decreasing now. Uh, uh, all these elements in our omega u are less than, in this curved sense, less than u. So ui less than u. So omega I equals k I omega. I. So ui omega. So the first thing. Now u I more than u j if I less than j. Yes, it is the meaning of the word that ui is a decreasing chain. So if I grows, then ui decreases in this general sense. Means that u omega j equals k I j omega I. Okay. Let me use my notes. Uh, Now. Let's say omega J is weakly compact. There exists a subset GM such that omega JM goes to some omega bar when M grows. I don't write goes to infinity because it is just in the sense becomes unbounded in I. Yes, now let us fix. So what my aim is, that U bar equals -1 of omega bar is lower bound and so we have already found some lower bound. Yeah. Yeah.
Omega U or of the chain?
Of the chain. Thank you. Mhm. To this end, so we have to prove that this omega bar is less than vorticity of any element of the chain. So let us say fix I, some element of the chain. Then omega Jn equals Kjm, Kijm of what? I omega. So we first move or transform omega into K I omega, it is omega I, and then transform omega I in omega Jm by this. Now, these operators, it is a fixed. It does not change it further. The set K I J M and no, in fact, M is element of other linearly ordered set, which is subset of I. Yeah. Is weakly recompact. Yeah, because it's set of measures. Set of measures as a set of corresponding operators is weakly recompact. There exists subsequence K I G J M with additional number P such that let me continue here. I G and E converges weakly to K I prime, which is element. No, in particular, K I J and P K I omega converges weakly when P goes to the same W bar. Some W bar. Converges weakly. But operation minus 1 compact as operator V0 to V6. Not integral operator. So this means that rho minus 1 of all this A, J, and P, with I, omega, converges already strongly in A2 to rho minus 1 of omega bar. And omega bar and this is rho minus 1 of I prime Rho mu phi. One moment. No, this limit, the limit of this. Uh, the limit of K, I, J, and P, when P is unbounded, let us denote it by K, I, R. And then we have the following, the K, I prime, K, I, omega equals omega bar. If you take the weak limit of this. And I will prime this polymorphism. K I omega equals omega I. And so we have that omega bar is less than omega I. So I prove no, okay. I think it takes some time just to keep all details of this in the open field of your mind. So let me say, so we proved that we found some omega bar, which is less than omega I. So then I. No, this means that U bar equals curve minus 1 of omega bar is lower down of the chain from the minimal element there is one more component. What happens with the energy? The energy of it is L2 norm square of L2 norm of velocity. velocity is obtained from vorticity by integral operator. So it's, as a result, in the space of vorticity, to space of vorticity, energy is compact quadratic form, kinetic energy, and being compact quadratic form, it is we can if the sequence of vorticities thanks to some limit in a weak sense, and the value of compact quadratic form tends strongly. Yes, like a numerical sequence. The limit, and if it was constant, constant for all elements of omega u, it will be constant in this limit. So this limit is it will be the same in this weak limit. So in this weak minimal element. Okay. So so this way. Now what is the next? Let me. What is the next? Next, we will study the properties. Yes.
May I ask a question? So, if I remember, the space of polymorphisms was just pre-compact. How do we know that Ki prime is a polymorphism? Don't we have to prove like some consequence?
Because the property of the polymorphism is a property which is stable under weak convergence.
Okay, so it is weak compact.
Yes. So because first being positive measure with integral 1 is stable with weak convergence, and having this projection on both coordinate 1 is also this property, because instead of project at a point, we can project and take integral of some smooth function, cylindrical function, depending on x or depending on y. Yes, and because we have weak convergence of measures, the integral will converge to the definition of weak convergence. Okay, so next we will study the properties of these minimal elements. Just to open a small secret, they are stationary solution of Euler equations. Yeah, so this will be explained next time. And the goal part. So I will try to cover my, so to say, first lecture in the space of 3 lectures.